All right, guys. So welcome to the video for chapter 12, lecture 2. We're finishing up the chapter. So as you remember, we went over IMFs, intermolecular forces, the last time. And they were dispersion, right, to begin with as the weakest. Dipoles next. Strongest hydrogen bonding is the strongest of the covalent bonds. And then you got the ion dipole, which is between an ion um, and a polar molecule, right? So remember, all these IMFs are important in predicting solubility and boiling points and melting points and the stability of molecules, right? So we'll continue with some properties that we can now explain by using IMFs. So the first one would be surface tension. And surface tension is described as the property of liquids that result from the tendency of liquids to minimize their surface area. So to minimize the surface area, liquids form drops, right? That's why every liquid will seem like a sphere, right? Because all of the IMFs is drawing, right? All the force of the IMFs is towards the center. Okay. So when you draw everything towards the center, everything outside curves, right? It becomes like a droplet. Surface tension is also this phenomenon um, that allows small insects to basically walk on water, right? And it's due to the hydrogen bonding, really strong hydrogen bonding between the water molecules. So suppose that these are water molecules, right? These blue balls. You can imagine that every single water molecule here has hydrogen bonding in every direction, right? So this interior water molecule, for example, has about 6 neighbors around it, and it has the hydrogen bond, right? That black dotted line, or the hydrogen bonds to 6 of its neighbors. Okay, so this interior water molecule is um, being pulled in every direction, right? But in contrast, the water molecule at the surface is only interacting with 4 neighbors. And where's the force? The force is lateral and also downwards. So you can imagine that it's like taking a saran wrap and stretching it over a bowl. And so the tautness of the surface is what surface tension is, right? And it's due to that hydrogen bond. Okay. So in order to break through the surface of water, you need some energy in order to do that, right? And that's what we call surface tension. It can be measured as an energy that it takes to break through the surface, right? And I'm sure you guys have done this, as kids or maybe as adults too. You like go belly flopping into the pool and it hurts really bad. That's surface tension, right? So surface tension acts like a layer of like elastic skin that allows you to float things, small objects on top of it, because there's some tension, right? There's some surface tension that needs to break through for things to sink into the water. Okay, but due to the very strong hydrogen bonds, the surface tension of water is quite high. So you can float even like a paper clip on water, right? I think I have a picture of that. There we go. Pretty remarkable because you have a solid. A solid is more dense than a liquid. So this paperclip has no business actually staying afloat, right? But it's only doing so because it has um, uh, uh, water, uh, hydrogen bonding of the water. It's helping it to do that. Okay. So surface tension can be measured. Um, it's energy, right? So it's going to be measured in terms of energy per area. So the surface tension of water, for example, is measured as 72.8 millijoules per meter squared. That's at room temperature, right? If you compare it to benzene, for example, which is C6H6, it's 28 millijoules per meter squared. So benzene has a much lower surface tension than water. Well, why? Already, that must mean that benzene has a lower IMF, right? Has a weaker IMF than water. Well, what IMF does C6H6 have? We only have CC bonds and CH bonds here, right? Those are nonpolar. So C6H6 has dispersion forces only for its IMF, and dispersion forces are way weaker than hydrogen bonding. And so that's why its surface tension is so much lower. Okay. You probably won't be able to float a paperclip in benzene, right? Even though you can do it in water, right? Let's talk about the factors that affect surface tension. Obviously, it's the IMFs, right? That's the main one. The stronger the IMF, the higher the surface tension is going to be, right? But also, if you change the temperature, you can also mess with surface tension. So let's think about it. If we raise the temperature, what we do is we increase kinetic energy, and the increased kinetic energy will weaken the hydrogen bond, right? Or the IMF, whatever the IMF is. And so the weakening of the IMF in these molecules will reduce its surface tension, right? So you can just generalize, but raising the temperature of any liquid will reduce its surface tension. Okay, so here's a picture. As you can see, liquids tend to form droplets um, due to the interior molecules, IMFs, kind of drawing everybody towards the center, right? So if you draw everybody towards the center like this, then you're going to form a droplet, right? Okay, so that's why liquids form droplets, right? It's also about IMF. Now, water, very remarkable because you have really strong hydrogen bonding. So here is a droplet of water uh, on the ISS, the International Space Station, where there is zero gravity. Right? So things are, you see how things in the background got to be tied down because everything just floats, right? Um, so there's no gravity for anything to stick to itself, right? So the only reason here why the water forms a droplet is due to hydrogen bonding, purely the IMF of the water molecules themselves, right? So it is the IMF, it's that force that binds all these water molecules together. Otherwise, they would be completely dispersed everywhere, right? In the ISS. But you don't see it like that. They actually just coalesce because of the very strong hydrogen bonding. And what shape is it? It's spherical. Because again, think about the water molecules that are in the center here. What are they doing? They're drawing all the other water molecules in with the hydrogen bonding. Right? So pretty cool, pretty remarkable, right? Okay, let's move on to the next property that also has to deal with IMF, viscosity. So viscosity is defined as the resistance of a liquid to flow. Um, and it's measured as a poise. One poise or one capital P is the same as 1 gram per centimeter per second. So you're measuring how much stuff can flow, right, over some distance per time. So it is really the resistance of a liquid to flow. And you've experienced this, right? You poured water out of a bottle, really easy to pour, right? And you've also poured like oil out of a bottle, right? So or grease, right? Grease is very hard to pour. Okay. So that all is what viscosity is measuring, right? How easy is it for the liquid to flow? Um, centipoise can sometimes be given too for smaller values. So water has 1 centipoise for its viscosity at room temperature. So this is how it goes. Think about it. How does IMF going to affect viscosity? Well, if you have stronger intermolecular attractions, right, stronger IMFs, then you should have a higher viscosity because um, the attractions between the molecules are much stronger, so they're not going to want to flow very well, right? They're not going to be able to have enough kinetic energy to flow. And so you get a much thicker, sort of higher viscosity liquid, okay? And here, this table compares several hydrocarbons from N-pentane to N-nonane. Remember what these pentanes, hexanes are. These are just carbon chains. So pent means 5. It's like a 5 carbon chain, 6 carbon chain, 7, 8, 9, so on. So we know that because as you go down this table, the molar mass increases, right? And what does that mean about the IMF? Well, first of all, what is the IMF that's operating in all of these hydrocarbons? Remember, CC and CH bonds are nonpolar. So we only have dispersion here, right? And remember that as you increase molar mass, the strength of dispersion forces also increases. And so what does that mean about viscosity? It also increases. Okay, so you'll find that you want to try and say pour octane versus pouring pentane, it's going to be much harder to pour octane, right? It's just kind of like comes out really slow, right? Due to a much higher intermolecular force. Okay, so in summary, the stronger the IMF, the higher the liquid's viscosity will be. And then shape also plays a role, right? Just like in dispersion forces, shape also plays a role. So the more spherical the shape is, the lower the viscosity will be. Because if you're a spherical shape, you're like a ball anyways, and balls love to roll, right? So they'll just roll past each other really easily, meaning um, uh, they're easy to pour, right? And so therefore lower viscosity. Again, it's because of the less surface-to-surface contact, right? Lowers the strength of the IMF, right? Lowers the dispersion force. Remember that? So then of course you're gonna have a lower viscosity. Okay, the factors that affect viscosity. Again, temperature. Temperature is gonna do that. What happens if you raise the temperature? Remember that the reasoning for that, right? If you raise the temperature, you raise the kinetic energy. More vibration means you're gonna weaken that IMF. Okay, so if you weaken the IMF, the viscosity is gonna be lower. Okay, just as you can see that in this table for the viscosity of water at several temperatures, you can see as you increase the temperature, the viscosity decreases, right? By quite a bit too, right? So again, the reasoning for that, your IMFs are being weakened by the increase in energy. And so if you have a weaker IMF, it's going to be easy for the molecules to roll past each other, and therefore the liquid's going to be less viscous. Okay, our third phenomenon, it's called capillary action. This is the ability of a liquid to flow up a thin tube against the force of gravity. Okay, so quite remarkable. You're like, how does it do that? How does a liquid actually travel uphill? So capillary action is the result of teamwork between cohesive and adhesive forces. Together, these two forces work together in order to make a liquid travel uphill against gravity. So what are these two forces? Just like how it sounds, cohesive, like co-ed or cooperate, means together, right? So the cohesive forces means the forces that hold the liquid molecules together. Okay. Adhesives, adhesive forces means the attraction between the liquid molecule to the glass of the tube, right? The tube's glass wall. Okay, so adhesive means two different things, right? Where co means it's the same thing. So adhesive force is one thing sticking to another, right? Like adhesives. Um, so that's how it works, right? So without those two forces, the liquid can't go up, right? So what happens is the cohesive force, and the cohesive force, by the way, is the same thing as IMF, right? Because it's the force that holds the water molecules together. So the cohesive forces hold the water molecules together, while the peripheral water molecules stick to the glass wall. That's the adhesive force. So together, they climb the wall, right? You have two forces there at work, right? The one that sticks to the wall, and then the one that sticks the water molecules together, which is the hydrogen bonds, right? Okay, so the thing that we see is that the narrower the tube, the higher the liquid will rise, right? And this kind of makes sense because the narrower the tube, um, the stronger the adhesive forces will be, right? And you need to be able to stick to the wall like Spider-Man in order to be able to climb up, right? Okay. The next thing, meniscus. So believe it or not, meniscus is also due to IMFs, right? You guys know the regular meniscus of water, which looks like a smiley face, right? This meniscus is called convex, okay? But if you were to look at mercury, put mercury in a tube, the meniscus is actually like a lump, like a little hill, okay? This is called, um, oh, sorry, this smiley one is called concave, right? Because that's how I remember it. There's like a cave, okay? And then this one is convex, okay? So the meniscus of the mercury is convex. So why is it like a frowny face and not a smiley face? Well, it has to do with IMFs. Um, so in the concave meniscus, why we see this lipping up on the side is because the adhesive forces are stronger than the cohesive forces. So water loves to stick to glass, okay? So that adhesive force kind of pulls everything against um, the walls, kind of like that carnival ride, the Gravitron, right? And everybody's like against the wall. And then there's like this, everybody else in the middle is like sinking down, right? So um that's the reason the adhesive force is stronger than cohesive forces. But in Mercury, it's the opposite, right? The cohesive force or the IMFs of Mercury is stronger than the adhesive forces. So all the Mercuries want to stick together, and so that's why there's like a lump in the middle. Okay. And that makes sense because the IMF for Mercury is dispersion. All right. And for glass are silicates. So we're talking like SiO2. Oxygen's an electronegative atom. So silicon oxygen bonds are polar. Okay. So that's why water loves glass, because glass is polar, very polar. Okay. But mercury doesn't like glass. Mercury's non-polar. Right. So mercury's like, oh, get me away from the glass. And so that's why it's forming that convex um meniscus. All right. So we're going to switch topics a little bit here. We are going to go into looking at phase changes and what is happening on the molecular level um, during phase change. And we'll go into vapor pressure and boiling point and all that. Okay. All right. So molecules, the molecular dance. So molecules in the liquid state are always in motion. Actually in the solid state too. I just can't move as much anymore. But they vibrate. But molecules in the liquid not only vibrate, they also can rotate and also translate. Translate meaning they actually move, right? You guys know what rotate is. You can rotate in one spot, okay? But you have a lot more motion, right? And we know that the average kinetic energy is proportional to the temperature. Um, so um, we we know that some molecules always have more kinetic energy than others, um, and others have less, right? Than the average. So let's talk about the phase change of vaporization, going from a liquid to a gas. So how is that happening? Well, if you have water in a beaker, right? The water molecules at the bottom of the beaker is not the one that's going to evaporate first. Okay. So if you analyze it, this makes sense, right? Because the water molecules at the bottom, remember, have more hydrogen bonds, right? Because it's surrounded by more water. So it's not going to be able to escape into the gas phase. However, the liquid molecules, the water molecules at the surface of the liquid does have enough energy because it's not tied down, right? It has fewer neighboring water molecules, so fewer hydrogen bonds, so that it can absorb enough energy to overcome the IMF, the attractive forces between its neighbors, to get into the gas phase. Right? And this allows them to change phase, right, from liquid state to gas, right? Remember, the only difference there is the distance between the molecules, okay? So in evaporation, think of the surface of the liquid that is going to be very important in evaporation, right? So how big the surface of the water is will determine how fast the water is going to evaporate, right? And go into the gas phase. Okay, so here's the distribution of thermal energy. So only a small fraction of the molecules in a liquid will have enough energy to escape into the gas phase. But as the temperature increases, that fraction also increases because now you've increased the kinetic energy of the entire everybody in the container, right? And so that makes sense. The higher the temperature, the faster the rate of evaporation because you have increased the fraction of molecules that will have enough energy to break free of the IMF, right? Okay, let's think about condensation in terms of IMF. Condensation's the opposite, right? You're going from a gas back down to a liquid. Okay? So think of a gas just randomly moving around, right? These particles. Well, as they're moving around, they will lose energy, right? Through molecular collisions. It'll slow them down a little bit. Because what happens when things collide? Um, there's a small bit of attraction, right? And so then they lose a little bit of energy. So the result will be that some of the molecules will get captured back into the liquid phase as it is losing its energy, right? And it's making more collisions. So some may and stick together to form droplets, and we call this process condensation. Right? So it is about the IMFs, how well things condensate or things condense, because um, when the molecules collide with each other, there is an attractive force. That attractive force is the IMF, right? Um, so if the IMF is stronger, it's able to go back into the liquid phase more readily, right? Than if it's weak. Okay, so evaporation versus condensation, they're just opposite processes. Um, and if you have an open container, say, of water, right, eventually all of the water molecules will escape into the vapor phase because um, you have, right, every time that the top layer of the water molecule evaporates, it exposes a new layer, right? And so that ambient room temperature will eventually um, evaporate all the water. If you want to evaporate the water faster, what can you do? You can throw the water on the floor, right? And the water, since it's spread out, you have greater surface area. Remember, it's the water molecules on top of the surface that's going to escape into the gas phase first. So if you spread it onto the floor, you're gonna make it, quicker to evaporate. Okay, now the interesting thing comes when you have a closed container, right? And so the gas molecules can't escape. So where can it go? Well, it can go up into this headspace. That's what we call it, right? It looks empty, but it's not. We know it's not empty. First of all, it has air in it, but it also has water molecules up there in the gas phase, right? Because with the stopper here, it can't just keep evaporating like in the open container. Okay, so the gas molecules will go into the gas phase, but then it gets stopped by the stopper. So now we got water vapor up here too. Okay. So you got three scenarios here. In A, this is, earlier in time, you just stoppered the flask. So immediately what you're gonna get is just the evaporation of water into this headspace. So that's represented by the upward arrows here is the evaporation rate. Okay. So first you only have evaporation. Okay. But then as you put water molecules into this headspace, they can collide with each other and condense back down to become a liquid. So you start to see small downward arrows now. Those are the rate of condensation. Okay. Some other time later, right, even more water gas molecules are up there. And so the rate of condensation grows as well. Until when? Until the rate of evaporation, the upward arrow, is equal to the rate of condensation. And this is where we have what's called dynamic equilibrium. Dynamic meaning this process is going forever and ever, right? You always have water molecules going into the gas phase. You always have gaseous water recondensing back down, but they're just doing it at the same rate, exactly the same rate. So you will always have the same amount of gas particles in the headspace and the same of liquid particles down here, right? So that's why it's called dynamic equilibrium. Here's another like a graphical way to think about reaching dynamic equilibrium, right? So again, at the very beginning, when you stopper the flask, you have the rate of evaporation, and it's quite constant because you have, a whole bunch of water in the liquid phase. And so it's just putting it into the gas phase, putting water molecules in gas phase at a very constant rate, right? So we call that the rate of evaporation, okay? It's the rate of condensation that changes because at the beginning, there's nothing to condense, right? There's no water vapor up there to condense. So it starts at 0, okay? But then as you evaporate more water, now there's water molecules in the gas phase bumping into each other and it's able to recondense. So the rate of condensation starts to creep up. And it does so until it meets the rate of evaporation. And right when those rates are equal, we call that dynamic equilibrium, okay? So what that means is it doesn't matter how long you leave the flask there. At one point, after it's reached dynamic equilibrium, there's only so much water vapor in that headspace, okay? And then now if you take a pressure meter, for example, and you measure the pressure here of the water vapor, it will be constant, right? And later you'll see that we call that the vapor pressure of water, right? Okay, so how does IMF then affect evaporation and condensation? Well, let's think about evaporation first, okay? In order for things to go from the liquid phase to the gas phase, it has to completely break the IMF, right? And IMF is pretty much obliterated. So if you have a strong IMF, it's going to be harder to evaporate. Everybody agrees, right? If you have a strong IMF, it's going to be harder to evaporate. And so therefore you have to put more energy into it in order to get it to evaporate, AKA you have a higher boiling point, okay? And we have a term for that too. If you can't be evaporated easily, meaning you have a high boiling point, you're called non-volatile, okay? It's non-volatile. But if you have a weak IMF, doesn't take that much energy to obliterate the IMF, and all of a sudden you're in the gas phase. So you're called volatile because you're easily evaporated. And therefore, you can also conclude that, you must have a low boiling point, right? If you're volatile. Okay, so we can actually measure this, right? Now, every molecule is going to be different because every molecule has its own IMF strength. That's why every molecule has its own boiling point, okay? But we can also measure how much it takes for, to get a certain amount of that compound to go from the liquid to the gas phase. And we call this the heat of vaporization, or delta H vape for short. It's the amount of heat energy required to vaporize exactly 1 mole of the liquid, okay? So it's always going to be in units of kilojoules per mole. And since you always need heat to vaporize, the delta H vape is always a positive number because it's always endothermic, right? You always require energy in order to do it. And it is somewhat temperature dependent as well, right? Because obviously it's going to be easier to vaporize things that are already warm than vaporize things that are cold, right? If you have 2 liquids, one is cold, one is hot, of course, it's not be easier to vaporize the hot liquid. And so that's why you see in this table where it has the heat of vaporization for several liquids and their boiling points, it has 2 columns, right? How much it takes to vaporize at room temperature and how much it takes to vaporize at that liquid's boiling point. So obviously, the column of delta H vape at the boiling point is always lower than the delta H vape at room temperature, right? So we can see by far here, water is the highest. Water has the highest delta H vape, the largest enthalpy of vaporization. Guess why? Because of hydrogen bonding, right? So very strong IMF. It's going to take much more energy to vaporize. So that's why it's at the top of the list, right? Okay, so again, notice, the units here, right? Kilojoules per mole, and also the difference in the two columns. Diethyl ether, if we draw that out, you'll see that it is polar, but it doesn't have a very big dipole. It's polar, but not like by a lot. And so that's why it is sitting down here in last compared to, say, acetone and rubbing alcohol. Rubbing alcohol, remember, is also hydrogen bonding because it has the OH group, right? And so that's why its number is very close to water. But since water has two OH bonds, right, it still has a higher delta H, right? Okay, so let's do this example problem together. Calculate the mass of water in grams that can be vaporized at its boiling point with 155 kilojoules of heat. Okay. So we can go to the board for this one. We got 155 kilojoules of heat. And we're asked how much water can be vaporized in grams. So we're going to go back to our table, and it says at the boiling point. So we're going to be the third column here. Looking at water, water has a delta H rate of 40.7 kilojoules per mole. Okay, so it's nice and easy calculation here, right? Start with what you're given, 155 kilojoules. And what's going to go on top? Well, you want kilojoules to cancel, right? So mole's going to go on top. So for 1 mole of water, it's going to take 40.7 kilojoules of heat in order to vaporize it. So how many grams of water is that? Well, 1 mole is going to be about 18.02 grams of water on top, right? Um, so that's going to give us 68.6 grams. Okay, so 3 sig figs because of that 155. Okay. Okay, you guys can do this practice problem here. Okay, pretty easy. So let's move on. All right, let's talk about vapor pressure now. Okay, so remember those 3 flasks, in the third flask that reached dynamic equilibrium, which means there's a fixed number now of, water vapor in that headspace. If you take a pressure probe and you put it to that headspace, you'll get a number. That is called the vapor pressure of water, right? So it's the pressure that's exerted by the vapor when it is under dynamic equilibrium. Yeah. So how does, again, IMF affect this? Let's see. If you have a weaker IMF, okay, that means the bonds between the molecules are not held on as tightly, okay? So it doesn't take that much energy to bring it into the gas phase. So therefore, you're going to have a higher vapor pressure, right? Because you're going to have more vapor. So you have a higher vapor pressure, and a higher vapor pressure correlates to a lower boiling point, right? Because you don't need as much energy to evaporate things. So that will result in a lower boiling point. And we call these kind of liquids more volatile liquids, right? Then the opposite's true, right? What if you have a stronger IMF? If you have a stronger IMF, then you're gonna have a lower vapor pressure because it's not gonna be as easy to vaporize. So you have a lower vapor pressure, which means a higher boiling point, and therefore a less volatile liquid. Okay, so let's see what happens when you disturb the dynamic equilibrium of a liquid. Okay, so let's look at these 3 scenarios. In scenario A, you are at dynamic equilibrium. Okay, so meaning the rate of evaporation, this upward arrow, is equal to the rate of condensation, so that there are a fixed number of gas molecules in this headspace. Okay, now what happens if you increase the volume? If you increase the volume, what you do is you decrease the pressure, right? Remember pervert, PV equals nRT? If you increase the volume, you decrease the pressure in this headspace. So the system will have to correct in order to bring everything back into equilibrium. So then it puts more gas into that headspace. So the rate of evaporation will increase if the volume is increased. Okay. What if the volume is decreased? Well, if you squish it now, that means you're going to increase the gas pressure in this headspace. And so to alleviate that increase in pressure, the gas molecules will condense. So the rate of condensation will increase. Okay. Pretty interesting, right? So this principle is called Le Chatelier's principle. Notice that that's actually how nature behaves. You put stress on anything, any system in nature, it will fight back. It will try to get back to, equilibrium or homeostasis, right? It's that idea, okay? That any system is going to resist change, okay? But in the sciences, in chemistry, in particular, we attribute that to Le Chatelier. So Le Chatelier studied a lot about equilibrium, and that's Le Chatelier's principle: is when conditions change, the system will shift its position to relieve or reduce the effects of that change. Okay, and so we saw that here, right? If you increase the volume, then you're gonna make the rate of evaporation faster, and then if you decrease the volume, then you make the rate of condensation faster. Right? Okay, let's talk about the temperature dependence of vapor pressure. So what happens when we increase the temperature? If we increase the temperature, we're going to get more kinetic energy of the liquid molecules, and therefore vapor pressure will increase, right? Because it's going to be easier to put them in the vapor phase. So actually, even small changes in temperature can make a huge difference in an increase in vapor pressure. And the rate of this growth, of course, is going to be tied to the strength of the IMFs, right? If the IMF is really strong, then the changes are going to be smaller, right? If the IMF is weak, then the changes is going to be bigger, right? So let's take a look at the graph that compares 4 different liquids here: diethyl ether in yellow, ethyl alcohol in cyan, water in magenta, and ethylene glycol in is light blue. Notice that what we see is as we increase the temperature, the vapor pressure increases. Okay. So no surprise there, right? We already know that. We can explain that. But what's interesting is this horizontal line here. Okay. At 760 vapor pressure. So 760 torr. Remember what that unit is. Torr, 1 torr is the same thing as 1 millimeter mercury, and 760 millimeter mercury is 1 atmosphere, right? So this line is telling us, okay, at sea level, what is the boiling point of each of these liquid? Is where the vapor pressure meets that horizontal line. Okay. So then we now have a scientific definition of what a normal boiling point is. A normal boiling point is when the vapor pressure of any liquid meets the atmospheric pressure at sea level, right? So that's why it's called normal. So of course, the boiling points of things can fluctuate, right, based on your altitude, right? So you can see that for water, where it meets that horizontal line is at 100 degrees Celsius. And so that's why we say water boils at 100 degrees Celsius. Well, certainly here, yes, because we're at sea level and we do see that, but it's going to change, right? If you change your altitude. So ethyl alcohol boils at around 78.3, diethyl 34.6, ethylene glycol at some much greater temperature. Okay, so the boiling point, what is it that exactly? We are defining it, right, again, as when the vapor pressure is equal to the external pressure, okay, is when you'll get boiling, okay. So you can see how boiling is reached, right? So if you are looking at, say, a flask on a stove, right? you can see that the bubbles are forming at the bottom. Okay. And that bubble is forming because you have increase in the kinetic energy. So the water molecule is kind of like making room, right? It's like going like this, and it's actually making little pockets. And those are what bubbles are. Now, if the atmospheric pressure is greater than the vapor pressure inside, it will smash the bubble. And so you don't get boiling. Okay. But as you add more heat, what happens? You increase the vapor pressure inside the bubble until it is equal to the atmospheric pressure. So it gets propped up. It does not get popped anymore, right? It can prop itself up. And then, of course, if it can sustain that, the bubbles will rise because it's less dense than the water. And so that's why you start to see the rolling boil. Okay. So that's the technical definition of boiling, is that when the vapor pressure is equal to the atmospheric pressure. Now, the atmospheric pressure can change, right? So the boiling point of liquids can also change based on altitude. Okay. So we know that when we go up in altitude, right, the air gets thinner, meaning the atmospheric pressure decreases. So what does that mean for boiling point of all liquids? At higher altitudes, they will also have to decrease. Okay. So for example, where we are sea level, right? So our water boils at 100 degrees Celsius, right? But if you go to the Mile High City, where we call that Denver, Colorado, you're gonna see that water actually boils at 94, which would be really weird if I was to teach chemistry in Denver, right? And I'm like, oh, water boils at 100, and nobody believes me, right? But yeah, it's truly it's kind of a problem for them there that their water doesn't boil at 100, right? Um, Now, if you go, let's say you go to Mount Everest, which is the highest peak on Earth, you'll see that water boils at 78. 78. It's warm, right? It's not, how's that considered boiling, right? It's actually just warm water. But you'll see that water is actually going to a rolling boil there. Okay? And that's because the atmosphere there is only 0.32. Okay. And we're defining normal boiling point as vapor pressure becomes as great as external pressure. So external pressure drops, so does boiling point drop. This is a big problem because why do we cook our foods? You want to kill the bacteria, right? But now you're boiling water. Your water is boiling at 78, but it won't get any hotter. So how's it going to kill bacteria? Right. So it poses a challenge for people that are living up at higher altitudes. They'll have to use like pressure cookers, or the people that climb Mount Everest. I mean, they're not even cooking, right? They're just eating like dehydrated food. But let's say you do want to cook food at altitude, you will need to either cook your food for a lot longer, but if it doesn't even come to a boil, you can't kill anything anyway. So you better use a pressure cooker, right, in order to do that. Okay, we're getting to the last part of this chapter. We're gonna do some calculations here. So we've been talking everything so far, just in terms of quality, right? Just qualitative analysis. Now we're actually gonna calculate how much energy is gonna be put in heating things or boiling it, um, or melting it. Okay. So first you have to learn about the heating curves. So heating curve of a liquid is shown here on the right. So you can see that temperature is on the y-axis, heat added is on the x. So let's say that you have a liquid at initially 20 degrees Celsius. So that's this data point right here. Okay. As you add heat, what happens? It'll ramp, right? So temperature will increase, temperature will increase, temperature will increase until, and this liquid, by the way, is water. Okay. So water at 20 degrees Celsius gets heated up, and then all of a sudden you add heat, but the temperature doesn't change. It just flatlines. Okay, that's weird. Well, I'm adding heat. Why is my water not heating up? Oh, wait a minute. Well, at 100 degrees Celsius, I'm no longer water, right? Water turns into steam there. Okay, so the way you can think of this flat line is a phase change. And how do you explain that it's flat? Well, all of the energy is going into breaking the IMFs, right? So not until all of your liquid turns into steam do you ramp again in temperature, right? Because all of the heat that is being added is going into breaking the IMFs until every single last water molecule is turned into steam, right? And then here, everybody's steam, and then you keep adding heat, and then it's just like hotter and hotter steam, right? Until you top out here at 140 degrees Celsius steam. Okay. Okay, so to calculate this, what you need is at every ramp, you have a change in temperature, right? And we already know an equation for that. Q is equal to MC delta T. So whenever you have a ramp, meaning you have a delta T, you can use this equation. Q measures the heat, remember? Is equal to the mass, so how many grams? Grab the specific heat of that liquid. It'll be water here, right? Then times the change in temperature. So for example, if you're looking at the first ramp here, the change in temperature will be, where was it from? From 20 degrees to 100. So final minus initial for delta T, right, is 100 minus 20, which is an 80-degree change in temperature, right? That's how you do it. We're gonna skip this here. This here is called the Clausius-Clapeyron equation. You guys can study it on your own, but just in the interest of time, yeah, I'm not gonna cover it. And so that also means if you encounter problems like this in the homework, you can skip it as well. And I'm not gonna put any of it on the exam. Okay. All right. So let's talk about what a supercritical fluid is. So let's say that you have a liquid that is completely in a sealed container, right? Very sealed container, very airtight. It's not going anywhere. And you just start heating this chamber. Okay. So this is the beginning. This is what would it look like, right? You have liquid, which is more dense, so it's going to be at the bottom. Then the gas is going to be at the top, and you can see the interface, right? So then as you heat this fluid, what happens is it's going to put gas molecules into this space, okay? Which means it's going to make the top space more dense, right? While the bottom phase gets less dense, okay? And since the fluid has nowhere to go, all you're doing is you're doing this change in density. So eventually what happens is the gas phase, the top part of the chamber gets more dense, and the bottom part of the chamber gets less dense until they are exactly the same density. So you no longer see this line, right? This division between a liquid and a gas. You just see this. It's all the same. This is what we call a supercritical fluid. It has reached a point that it is no longer distinguishable as a liquid or a gas, right? So really interesting result, right? What a supercritical fluid is. Okay, let's talk about a critical point. The critical point is the temperature required to produce a supercritical fluid, right? So to produce this, you need a critical temperature and you need a critical pressure. It can't just form at any given moment, right? Uh, not until you reach the critical point, which is some critical temperature and some critical pressure, are you able to make a supercritical fluid. So the critical temperature or higher temperatures, or at the critical temperatures and higher, the gas cannot be condensed to a liquid, no matter how high the pressure gets. Okay, let's talk about another phase change, sublimation and deposition. So sublimation is a process where a solid goes straight to the gas phase, skipping the liquid phase. That's called sublimation. And deposition is the opposite. It's when gas molecules go straight to the solid phase, skipping the liquid phase. So they are, opposite of each other. Okay, let's talk about melting, or AKA fusion. Same thing. Melting is going from a solid to a liquid, right? And when you're going from a solid to liquid, you are increasing the kinetic energy by adding heat, and that heat is loosening the IMF, right? It's not breaking it completely because it doesn't need to go into the gas phase, right? But it does loosen it so that the molecules can roll past each other. And that's what we associate with the liquid phase, right? Okay, let's take a look at the heating curve of a solid. All right, so here you still have water. Okay, so solid water we call ice, right? So first data point here is at -10. So water at -10 is in the solid state, so we'll call that ice, right? So ice, as you add heat, the ice is gonna get warmer and warmer and warmer and warmer until boom, oh, it hits a flat. Remember what I said about flat? Anytime you see a flat, that's a phase change. Well, a solid is gonna melt first, right? So that we know that's the melting, that's not boiling, right? Because we're at solid here. And it's also at what temperature? 0 degrees Celsius. So we know that's where melting occurs for water. So here, why do we have a flat and no change in temperature? Because all of the heat being added is going into loosening, right, the IMF so that ice can turn into water. And not until the last bit of ice turns into water does the temperature creep up again, right? So here what you have is an increasing heat, adding heat increases the temperature of the water, right? So you get colder water, warmer water, and so on, right? Again, whenever you have a ramp, okay, you're gonna use Q is equal to MC delta T because it has a change in temperature there, okay? Okay, so just like with the delta H vape, which measures the energy that's required to vaporize a liquid, you also can measure what's called the heat of fusion, which delta H fuse measures the amount of heat required to melt 1 mole of a solid, right? Again, because melting is requiring energy, it's an endothermic process, a process. So delta H fuse is always going to be a positive number. And again, it's also slightly temperature dependent. Okay. So here's that same table with the 4 liquids, and here are the delta H fusion for each. Okay. So notice that the delta H of fusion um, kind of correlates to with IMF, but not as much as boiling point. Because here, right, the delta H fusion is of water is actually a little bit lower than diethyl ether. Okay, so this graph shows both the delta H vape and the delta H fusion of these 4 liquids. Uh, what just, you know, uh, what do you see right away, just screaming out at you, is that the pink bars are way higher than the blue bars, meaning that the heat of vaporization is so much higher than the heat of fusion, regardless of what liquid you are, right? So we can ask why. Why is that? Why does it take so much more energy to vaporize than to melt? Okay, right? Can we see why? Why does it take so much more energy to vaporize than to melt? Well, what is involved in each process? In melting, you only have to loosen the IMF, right? You only need to put enough energy to loosen the IMF. However, in vaporization, what do you have to do? You have to put enough energy in order to completely break the IMF, right? So of course, delta H vaporization is always going to be a lot higher. Okay, so now what we do is we put the two heating curves together of both the solid and the liquid, and we get the complete heating curve of water. So in this picture, let's look. Temperature axis is always gonna be Y, okay? Heat addis is X in kilojoules per mole. Our first data point here is at -25, and our last data point is 125. So at -25, we have ice, right? Because this is H2O here. At -25, water is a solid, called ice, okay? And then at 125, water is steam, okay? It's in the gas phase. Okay? So it's gone through 2 phase changes, right? And so let's track it. from negative 25, when you add heat, you're going to warm the ice cube until it hits 0. And then the ice cube stays the same temperature, right? So there's a flat that's melting. So the ice cube stays the same temperature, but it's turning into liquid. And until everybody's a liquid, then you see a ramp again. So in segment 3 here, you are warming up water, okay? Warm up water until it reaches 100. And then it flattens out again. Why? Because 100 degrees Celsius is the boiling point. So all the energy is turning the liquid water into a gas. Okay, turning water into gas, to boom. All of the water has been turned into gas, and then you start to heat up the gas. So we have colder gas, hotter gas, right? So 5 segments total when you look at the complete heating curve. Segments 1, 3, and 5 are ramps. So that's where you do what equation, guys? Q is equal to mc delta T. Okay, so let's put that on the board. Anytime you have a ramp, ramps, Q is equal to mc delta T. When you have a flat, then it depends on the flat. Q is going to be equal to mole times the delta H fusion at melting. Your flat is melting. If it's boiling, then it's mole times the heat of vaporization. Right? So 2 different values that you can look up. And we'll call this boiling. Okay, so those are the 2 equations. That's it in order to quantify how much heat you need in order to heat things up. Okay. Okay, so let's do it. In segment 1, we have a ramp. Okay, and notice that the ramp is going from minus 25 to 0. So it's Q is equal to MC delta T, where 0 is the final temperature, minus 25 is the initial, right? So you got our delta T. The mass of water. If we're going to do 1 mole of water, the mass of water is 18.0 grams, okay? And then we have to multiply by C, right? Q is equal to MC delta T. The C of specific heat of ice is 2.09 joules per mole per degree Celsius. Okay, so that goes there. Times delta T, right? T final minus T initial. So it is 0 minus negative 25 for a positive 25. So then your Q is going to be, if you enter this in calculator, 941 joules or 0.941 kilojoules, right? And you really should see for yourself that these are the numbers, right? You want to make sure that you know how to get this. So go ahead, punch it into your calculator and check that you have this number. Also, this is going to be one of the problems on the next exam. Right? Probably a long problem or at least a short problem. Okay. So make sure you know how to do it. Segment 2 is a flat, right? That first flat is always melting. Okay. So we're going to do Q is equal to mole times delta H of fusion. We can look up the delta H fusion in that table, right? Remember the table here? 6.02 for water, right? We are talking about water here. If we were talking about, acetone, then we'd grab a different number, right? So pay attention to what the problem's asking you. Now, moles. How many moles are we doing? 1 mole. So we're doing 1 mole times 6.02 kilojoules per mole. So segment 2 costs 6.02 kilojoule, right? It's a cost because it's plus. You need to put in, it's endothermic, right? Put in that much energy. Segment 3, again, is going to be a ramp. See? Ramp. Now, notice where it's ramping from 0 to 100. So you got your delta T there, okay? So Q is equal to MC delta T, right? M is still 1 mole of water, which is 18.02 grams. But now the specific heat of water is going to change because before it was specific heat of ice. So remember, these numbers change. So grab the right number. It's now 4.18 for the specific heat of water times the delta T, which is 100 minus 0. Okay, so we're going to get 7.52 kilojoules. Okay, now on to segment 4. Segment 4 is another flat. But now it's a boiling, so we make sure that we grab the heat of vaporization and we go mole, right? Because vaporization is in kilojoules per mole. So specify how many moles you're doing this with. It's 1 times 40.7 kilojoules per mole. So you get 40.7 kilojoules for segment 4. And segment 5 is another ramp. We're ramping from 100 to 125. Okay. So Q is equal to MC delta T, right? M is still 1 mole of water. Is the mass of that is 18.02 grams. But now we change it to steam's specific heat, which is 2.01 joules, right, per gram per degree Celsius, times the delta T. So 125 minus 100, right? That's your delta T. Okay. So you get Q is equal to 0.904 kilojoules. So now that you got the Q for all the segments, what do? Just add them all up. Okay, that'll be your Q total for the entire process of heating ice from minus 25 degrees Celsius to steam at 125 degrees Celsius. All right, pretty straightforward, right? As far as the calculations go. All right, let's do this one. Finding the heat of a phase change from heating 85 degrees Celsius of water, looks like here's water, right? To 117 degrees Celsius H2O. Well, H2O at this temperature is a gas, right? So first, what you want to do is make your diagram, right? Make your diagram here. Start at 85. You ramp. This is water, right? So where's it gonna hit the flat? Where's it gonna hit the flat? Where's boiling for water? 100 degrees Celsius. Okay, so you do have to map this out step by step. Okay. Then you're gonna warm it up to, the problem says 117. So that's where you add 117 Celsius. Okay. So actually this problem's shorter than the last one. You just have 3 segments. And remember, segment 1 is a ramp. So you use Q is equal to MC delta T there. And it's saying, let's see, the problem says, it wants to see what the heat is, heat total absorbed or released, 124.3 grams of water undergoes this, right? And then it gives us all the constants here. Okay, so what I would be doing on the board, I'm grabbing these numbers here, all right, on the table. Alrighty, so 24.3 grams of water. That's gonna be our mass. What is the specific heat of water? Oh, I see that the specific heat of water in the liquid phase is 75.4 joules per mole per degree Celsius. Shoot, it's joules per mole. So I have to take my 24.3 grams and turn it into moles. So I have to go 1 mole of water is 18.02 grams. So what am I gonna get here? .349 moles. Okay. All right. So, yep. Notice the units. Maybe you have to change it to moles, right? So it's either going to be in grams or moles. So now I'm going to use 1.349 moles times liquid water is 75.4 joules per mole per degree Celsius times delta T. Okay. So the first ramp is going from what? 85 to 100. So 100 minus 85 degrees Celsius. So degrees Celsius will cancel. Well, we'll cancel and I get just joules. So Q1 is gonna be 1525 joules or 1.525 kilojoules. Then segment two, Q2 is gonna be equal to mole times the enthalpy of, this is boiling now, right? Because we're going from liquid to gas. So we better graph delta H vape. So the moles is 1.349 moles times delta H vape is 40.7 kilojoules per mole. So Q2 is going to be equal to 54.9 kilojoules. Segment three, Q3 is a ramp. So again, it's back to MC delta T, but it's moles, right? So actually NC delta T for this particular problem. The moles is 1.349. Now grab the specific heat of gaseous water, H2O gas. That's 33.1 joules per mole, 30 degrees Celsius, times delta T. So what is delta T for the third segment? 117 minus 100 degrees Celsius. So degrees Celsius cancel, mole cancels. Q3 is equal to 759.1. All right, so if we add these together, Q1 plus Q2 plus Q3, what do we get? Let's do it all in kilojoules. Oh, wait a minute. Let me see, my Q3 may be off. Let me check. Oh yeah, this is joules or 0.7591 kilojoules. Yeah. Well, this was in joules. Okay. So my answer is going to be 57.2 kilojoules with some fix. Right? Okay. Yeah, so make sure you practice, and not with just water. You can do it with other liquids too, right? And all the constants will be given to you, including if it's not water, it will also give you the melting point and boiling point so that you know where the flats are, right? Of course, if it's water, you guys should already know boiling points and melting points for that. And so those will be given. Okay. The very, very, very last thing that you guys are in charge of knowing is the phase diagram. These are actually really cool. So the phase diagram is a diagram that shows on the y-axis the pressure, the x-axis is the temperature. Okay, it shows how the phases are in relation to each other, right? Because the two factors that govern phase change is temperature and pressure, right? So in a phase diagram, you can chart basically what pressure and at what temperature for a certain compound is it going to be a solid, a liquid, or a gas. Okay, so here's the phase diagram for water. We know water very well, right? So we know that water is a solid below 0 degrees Celsius. Okay, but it also has to be at a certain pressure because at 0 degrees Celsius, and if the pressure is really high up here, then water is actually a liquid, right? So you notice that these lines here is what separates the phases. So your fusion curve separates your solid from liquid. Sublimation curve separates solid from gas. And then the vaporization curve, this boundary here, separates liquid from gas. Okay. So basic you only need to know the basic of how to read a phase diagram. Obviously, know if I give you a pressure and a temperature, tell me what phase the thing is in, right? So let's say I'm like, okay, at 760 torr or 1 atmosphere, and we're at 200 degrees Celsius. Well, obviously, it's going to be in the gas phase, right? It's over here, okay? Um, or if I say, okay, if we're at like negative 100 degrees Celsius, um, and 600 torr, okay, then it's a solid, right? Okay. Um, two other dots that you need to know, or two other things you need to know, is the triple point and the critical point. The critical point we already talked about, right? Remember, it's the critical point is um, the point in which above that pressure and temperature, a supercritical fluid can exist, right? Now the triple point is super interesting. It's the point where all three of these curves meet. So what that means is if you're sitting here, which is for water, just slightly above 0 degrees Celsius, maybe 5 degrees Celsius or so, and you're less than atmospheric pressure. So I don't know, I would say 550 torr or something like that. You can reach what's called a triple point where all three phases are occurring at the same time, right? Which is really interesting thing to see. And I'll show you a video in a second of what a triple point looks like. It's as if the compound's confused. It's like, should I be a solid? Should I be a liquid? Should I be a gas? Right? It's really interesting. Okay, so just know how to find the triple point, right? Kind of describe where it's at. And really that's it. Okay. So here's other substances. Here's iodine, right? So oh awesome. Ooh, sorry. Couple more things you should know is how to determine a boiling point and melting point from a phase diagram. So a melting point, right, is where the melting point at say sea level. Okay. So go over to 760 torr and then see where the solid and the liquid curve meets and then extrapolate down to the temperature. That will be your freezing point. Okay. If you want boiling point, then at sea level, then take 760 torr all the way over to where the vaporization curve is, okay, where it meets, and then extrapolate down. What is that temperature? 100. Okay. So that's all you need to know. Let's try it for iodine. What if we want to know the melting point for iodine? So we find 1 atmosphere here, right? And we walk over to the um, the fusion curve, okay? And then we look down, okay? It's going to be a little bit past 114, so maybe 116, something like that, okay? What if we want to know the boiling point of iodine? So we're going to go from 1 atm over to the vaporization curve, the one that separates liquid from gas, right? Because that's boiling. We see that it boils at 184. Okay. Um, and then identify the triple points, right? It's like where all these three meet, and that's the critical point. Okay. Yeah, so really that's all you really need to know for phase diagrams, and this completes chapter 12 for us. All right, so I'll see you guys next time for chapter 14, which would be our last lecture as well.